No, just quickly, because we're not doing it yet.
Okay, all right.
Yeah. Just to quickly show you what's going on. So the JFET circuit is here. I have a table here that changes a value for a specific resistor to change VGS. Does that make sense? By controlling VGS, I am controlling ID. Remember, this is a voltage-controlled device. In the end, I ran this whole thing, and I show how to make the table. I ran VGS versus ID. And it looks like exactly like the transconductance. You'll have to prove it. Does that make sense? You'll have to pick a few points, see if it fits in the equation of the transconductance. Got it? So you can pick 2 points right off the table, put them in the transconductance formula, and see if they're 0 equals 0. We're good to go. Does that make sense? That's how you prove backwards engineering, right? So if you're given characteristics and already some table data, go backwards. But before you do that, you need to run the lab to get familiar with how this actually works, and you should have similar data based on the similar transistor. Does that make sense? But there are no guarantees. Why is that? If you didn't really in the lab.
Because every single one's different. Such a big
The pinch-off voltage could be slightly off from one another. Does that make sense? And we get to see the pinch-off voltage is in the voltage right here, this VGS versus ID. And the highest level of current is IDSS. Does that make sense? Okay. And again, I'll go through this analysis. That's when I turn off the light and do a sim. That's what we're going to do after what I'm going to do now. So I'm going to go over here. And because we still have one video to look at, which is this one. Key takeaway from it. Yeah. Yeah.
I like that age.
Yeah. Yep. And a key takeaway is depletion and enhancement as well. Does that make sense? So make sure you understand every time you're watching a video, what are the main objectives? What's the key takeaway out of it? You got it? Okay. All right. Well, let's run this one, and now we'll have questions.
You can't skip this ad, but you can skip the line. Go to vote.org to learn how to vote today.
Yeah, go ahead.
Switching off. On Muir, the Innovation Workspace, teams work.
Today's Back to Basics topic is an introduction to the field effect transistor, or FET. And we'll talk about JFETs and MOSFETs and different polarities, N channel and P channel, and the different types, depletion mode and enhancement mode devices. We're just going to cover some of the basic characteristics of FETs so you can understand what you're looking at.
So as you can see now, it's getting a little more complex. It's no longer just a diode or a transistor, right? And there are a lot more. There are a lot more semiconductor-based components out there we use for electronics. But these are popular because we could use them for switching and amplifying just like transistors. But you need to understand what their limitations are. Does that make sense? And sometimes what's the advantage of using them? Especially if you have a signal that is voltage driven that you want to control something with, like a toy or something. Does that make sense? Instead of current driven. You could use one of these guys. But notice here, we have two types, JFET and MOSFET. Okay? And your duty is to figure out what do these letters stand for. Got it? Okay. And then understand the difference between N channel and P channel. Right? And graphically, because that will be on the quiz as well. And then understand the difference between depletion and enhancement. So far, everything we've done is depletion. We stop from a point and just go down. Does that make sense? Enhancement, you stop low and you go up. So we'll get to see that in a minute.
Yeah, when you find them in the wild. When we talk about an FET, we talk about the channel. The channel really refers to the path between the drain and the source terminals of the device. And we'll see how we apply that a little bit later. A good analogy that helps people to understand FETs is this pinched garden hose analogy. Picture a garden hose with the drain and the source here. Water flowing through the garden hose is like the current going through the channel, where the hose is the channel. And then the voltage on the gate with respect to the source determines how much we're pinching off that garden.
We're good with that concept, with that model?
Yeah.
Okay, good.
Nodes and restricting current flow. Talk more about the operation of a FET in a moment. But let's first take a look at the FET family tree to understand how the types and polarities and modes all relate to each other. So the first major distinction is between the JFET and MOSFET, or the junction or metal oxide FET. We'll cover details of the differences in construction between these two shortly. Under the JFET, all JFETs operate in what's called the depletion mode, which means that without any bias between gate and source, the channel conducts.
And that's something we're going to be doing in the lab in a minute. Does that make sense? We're going to show starting our measurements from that point. In other words, VGS is 0 to ground. Does that make sense? In other words, RS will be 0 ohm, since I'm going to use RS as my flipped voltage for VGS. We'll get to see again the circuit analysis for that.
Current. And then by bringing the gate down below the source voltage, we start to close off and control the current or shift the current down. The MOSFETs can be built either as depletion mode or enhancement mode devices. The vast majority of the MOSFETs that you find are going to be enhancement mode devices. Enhancement mode means that the channel.
So this is going to be the key difference between enhancement and depletion. Let's redefine depletion. We started out with the channel max current, IDSS. Do you agree?
Mhm.
When VGS was 0. Does that agree? Okay. Yeah. Oh, okay.
It essentially does not conduct current when there is no gate to source bias.
So what happened now? It's an open circuit. It's the opposite. You with me so far? Now, that does not mean the depletion mode device with IDSS is a short circuit. No, there is a resistance there. You got it? But we will put an RD, a resistance at the drain, to limit the current. And you will see that when we do the lab as well. And RS also serves as a current limiter as well.
And then you change the gate voltage with respect to the source to enhance the channel and allow it to start conducting. The depletion mode MOSFET behaves very similar to the depletion mode JFETs. While you can also have depletion mode P-channel devices, I don't know that I've ever seen one in 30 years in the industry. There are N-channel depletion mode devices, but they're not very common as compared to their enhancement mode brethren. Again, we'll cover the depletion mode operation and enhancement mode operation here shortly. But I just want to kind of give you the family tree to kind of understand where all these terms fit within the family.
Any questions up to this point? We understand the family tree between JFET junction based or MOSFET metal oxide, right? Right? But I need you to read in your textbook, what the heck do they mean by metal oxide? Why? Does that make sense?
Mhm.
And why the other one is a junction, so it's like a transistor. Does that make sense? Okay, good.
Now, regardless of what we're talking about in terms of FETs, they all have some key common characteristics. That the gate input draws virtually no current, just a very, very small amount of leakage current, has a very high input impedance, and they're typically very efficient in switch applications.
Two very important points. Why would I want to use this stuff? One, the input impedance is extremely high. From looking at it from the gate, you with me so far? The input impedance of this device in AC or DC is going to be very high looking at it from the gate. Got it? And they're very efficient for switch application. Not as efficient, we've seen an example in the previous video, in terms of amplification. We only had about a 3-time amplification there. And again, this is not a current device driven device, control device. Do you agree? But still, there's more output signal than the input signal. Okay.
Applications. And there's certainly a lot of other characteristics too. Certainly, there's been chapter and verse written around FETs, but these are the major differences compared to, say, bipolar transistors. So let's dig into how these FETs operate. So the first thing we'll talk about is the difference between depletion mode and enhancement mode. And again, depletion mode means that the channel is already filled with carriers when there is 0 volts between gate and source. And then we control that current by depleting carriers out of the channel as we change VGS. Enhancement mode devices means that the channel is void of carriers when we have a 0 bias on gate to source. And then we control current by enhancing the channel with carriers by changing VGS. So this table might help with the understanding for depletion and enhancement mode devices. This table is kind of written around N-channel devices. So for an N-channel depletion mode FET.
So just quickly, look at the diagrams. What does this look like?
Reverse.
That's the transconductance, isn't it? Right? This is VGS versus ID. And if you notice here, this is what we're going to be doing in the lab. So we're using a depletion type device. Enhancement, on the other hand, the more VGS you have, the more ID you will have. You with me so far? You started out with no carriers and then you keep going from there. Here it goes backwards. The more negative voltage you have at the gate, the less current you have between the drain and the source. Once you understand these two, you're good to go. Got it? Okay?
You said the more negative.
More negative voltage you have for the depletion, the less current you have between what? The drain and the source, or ID, the current through the device. Okay? Right? We'll get to see that. So I'm going to stop here because I don't want to go through all 20 minutes of this video. Guess what you're going to be doing?
Watching.
You're going to watch it. You're going to carefully watch it. You see how it starts? It's very easy. It's always the same level. I like this video.
Yeah.
They don't try to go too complicated or too low in terms of understanding. So they respect the rhythm. So I carefully try to pick my videos here. What I'm going to do now is the actual simulation lab. So you get to see how it's done step by step and how I put the tables together and so on. And I hope I have Microsoft Excel here. If I don't, I'm in trouble. It doesn't matter. I have Open Office, I think. So let me just go over here and go to modules. So this is the lab we're doing. Click here. Doesn't matter. I know what that circuit looks like. Let me make sure I have Excel. I don't have Excel, but do I have Open Office? And I'll collect the data. You'll see. You'll have to trust me that the graph will be the same. So I'm going to go with the lab straight up, and let's go over here. And I'm going to start with a new one. I am going to pick a JFET. Okay. So let's see here. Here's a JFET. And I'm going to say, okay, here he is. Reduce it a little bit. I'm going to put some resistance right here. And then another one here. I'll explain why. Then I'll do my drawing right here. And then if you have Excel, you could fill the data for me. Does that make sense? I'll tell you which ones, and then we'll do it on the board as well. Come on now, stick in there. Go. Here. Here. Make this my ground here. Oops. Okay, so I'm going to call this one RS or RD since it's going to be at the drain. And this one, I'm going to call it RS. So before I start, I'll explain a few things. So we have to make sure we understand this. And let's say we start with 10 ohms. And this one at 0. And that's how I'm going to start this. And I'm going to put a power supply. Let's see here. Voltage. I'm going to put a 20 volt here. All right. And let's pick our transistor.
What's the R1?
I'll change it. Hang on a second. And we'll pick the 3919. Is that what I had? I think I did. And let me go back to this one. This is RD. There you go. So I have RD, RS. Is everybody with me so far? So I'm going to do a little bit of analysis. Let's say it's not zero. So don't worry about the zero yet. So say you have an RD here. You good? You know this transistor is going to be in depletion mode. What does that mean? That means, at least at minimum, if this was zero indeed, then this is a single wire. You agree? And if it is in depletion mode, that means I have maximum current going between the drain and the source. Let me put a D and an S there as points, because my voltages will come up accordingly. So D will go here. This will be gate, and this will be source. So we change this to the gate, and this to source. So we know that Vx voltage from here to here is going to be 0 because the resistance is what? 0, right? So I'll have maximum current going through here. I only have that resistor there just to limit the amount of current. Do you agree? I can take it to 0 as well and see how much real maximum current this thing can handle at 20 volts. That you can experiment if you want to. I'm leaving the 10 ohm in there to start my lab anyway. Got it? So, what happens? Well, I'm going to have a table here where I'm going to have various RS values starting at 0, maybe 1, 5, 10, 100, 200, 500, 800 ohms. Make sure you put your units. And let's say 1K, 2K, 10K, 50K, 100K. And I'm interested in what is VGS, what is ID. These two are going to be my transconductors. Do you agree?
Yeah.
And we get to see what they do. And I can measure everything else if I want to, but these are the two ones that I'm interested in. With me so far? Okay, so at 0 ohm, yep, come in. Yep. Okay, good. At 0 ohm, let's see what happens. What did I just say? That this point is same as ground, so is this one. So VGS is 0. And since we're in depletion mode, then we'll get IDSS. Does that make sense for this? So if I run this and DC up and say OK, and there you go. So let's see what values we're getting here. So what are we getting? VD is voltage from here to here. Is 19.8. What does that mean? That means I have a small voltage drop here, right here, 0.3. Do you agree? Or 0.2. Right? It is resistive. It's not a short. You with me so far? It has some resistance. If you want, you could track this, which I did in my lab. You can track this and notice, let's run it BD. Now, what would be VDS? It's equal to VD minus VS. You with me so far? And then you can track the difference. So what are we getting here? We're getting 12.1 milliamp. And this is in milliamp. What are we getting for VGS? We're getting, where's VGS? VRS. So let's see here. Did I say this? Yep. Right, G. Yeah. Hang on a second. Let me see if it took into action this part. Let's run it again. Okay. Did I put the points? I didn't put the points. That's why I don't see the points. They're not in there. Okay. Okay. Let's see here. I don't see the points right here. This should indicate that these are points. Ah, it didn't put it in. All right, so let's stop. Did this stop? Okay. So let's back to here.
Wait, I don't want to access that specific system on LT Spice.
Which one? The one in my lab? You could use any JFET.
I was like,
It doesn't have to be that one. As long as it's a JFET of the same type. You with me so far? So somehow in my circuit, let me just delete here. With scissors. Let me just put the points back. D. Point. And put it there. Put it there. Edit this to be gate. Edit this to be source. I might have put it in an empty space. Let's run it. Still getting that. So VD, yeah, I'm getting VD, no problem. And
I think it's just not showing the other two because they're at 0.
okay, all right. So we're going to go beyond 0 and see what happens. So right now at 0, we have 0 volts here, 0 volts here for these two. Does that make sense? Would you trust me if I told you it's 0 volts?
Yeah.
Yeah. Okay, good. All right, so we'll work with that. All right, so we know this is going to be what? 0 volt. And what are we seeing for VD? 19.87, which really means what? 20 minus 19.87 is the voltage drop from here to here. You with me so far? Just like VCE, very tiny. You with me so far? That's because that slab of material has some resistance. You with me so far? It's very small. It's not really a short. You with me so far? Does everybody understand the physics behind this by looking at what's going on? Perfect. Now, let's go ahead and add a little bit of resistance. Let's go for 1, 5, and 10. So I'm going to go back here. Change this to 1 ohm.
Wait, so VS is our source.
Yeah, so V1 is our source.
I understand. But when you're in your equation,
What you mean the source voltage? Let me call this VCC, just so.
because within your equation, VD minus VS, I understand that VD is the voltage.
Yeah, so VD is the voltage from this reference
Yeah.
to here. And VS is from here to here. The difference is this right here. Right. Okay. So, yeah, Kirchhoff. Does that make sense? Yep. So let's go ahead and run this with 1 ohm. Now, with 1 ohm, we should see a difference, a slight difference, but not that much in the current because, right, so we're not resisting the current as much. Okay, good, right, so the other points showed up. So we're still at 19.87, actually almost 88. But this time, notice I'm at 12.0 exactly. So I did lose some current, but not much. Does that make sense? And my VGS, which is VS, this will be negative, minus 0.01, right? Because this voltage, VGS, is pointing this way. But as far as we're concerned here, this negative is this way. So if we're looking at VGS, then it's negative of VS. You with me so far? So that's going to be a minus 0.012. Or even if you could put 121, if you want to be that precise. Has everybody seen how I'm doing this? So I need enough points to see if I can get that transconductance with this. So that's why I have all these values that I have on the board here. So I'm going to go back, okay? And notice I spent a lot of time here just to see how it is there. And I should have a little more here just to see how it is at the end. Would be so far? We get to see this is pretty predictable in the middle. But at the end, you want to really get the curve. You got it? So you may want to add more resolution there, right? So maybe instead of going from 50 to 100K, 50, 80K, then 150K. Does that make sense? And then put a meg on just to see what happens. You're not going to reach zero exactly. You with me so far? As far as ID is concerned, it will tend to go towards zero. It's pure physics. You're pinching, but there's still something leaking in there. You with me so far? Right, there will be always a leak. It will be very tiny, but it will be there. So let me jump to 100 and run it. And with my run at 100, notice here I have minus 0.7. And my current, I have 5 years, you can see. And my current in milliamp is 7 million, 7.1 million. This is volts, and this is in volts. And this one is at 19.92 or 93. And you can figure out 20 minus 19.93 is VDS. Does that make sense? Notice the bracket I have here. I'm interested in the transconductance. So yeah, I'm collecting data for everything, but these two are going to be more significant to me as to what my objectives for the lab is. Does that make sense?
So using the transconductance.
So I can draw the transconductance and see what it will do. Does that make sense? And then I can test it every time with actual to see if the formula works. You got it? You pick a point. That's your operating point. And then see if you're getting your coordinates. You got it? Okay. So, okay. What else? I'm going to jump to. So when I let you loose, what are you going to do? You're going to go work on this thing. Right. So I'm going to jump to 800. You don't do that. You're going to go and at least do what I have on the assignment. You have those values followed. And you can see there are plenty of points to get it done. So with this, at 800, we could see now that we have minus 1.7. And our ID will be 2.1 million. Actually, almost 2.2. This is 19.99. And obviously, you have 20 minus 19.99. You really have a fraction of a voltage drop against VDS. Let's put 10K. At 10K, I'm getting minus 2.5. And the current is 0.2 milliamp. Does that make sense? Right, so I'm going to go even further. I'm going to go 100K. And now you're going to tell me what you're observing, right? So, oops, didn't take it. 100K. And we're getting to 2.8 minus 2.8. And the current is going to get smaller. And it's 0.02 or 0.03 milliamp. So I'm going to go to 200K. I'm going to go beyond this. So let's go 500K. Heck. And run it. At 500K. I'm at minus 2.9. And the current is 0.005 milliamp. Actually, 6 milliamp. So, if I had to draw this. Yep.
What are you using to like to tell what ID is? Like, what are you
Right here.
Okay.
Right here. Does that make sense?
And then VGS is VS.
Yes. So VGS is the inverse of VS.
Okay. Oh, okay.
Right. So I'm picking up its negative in reference to gain. You got it? Okay. So if I were to draw this, now you need to figure out your scale. So this would be VGS, negative, and ID. We know the highest one we had was what? 12? So 12 milliamp right here. So 6 milliamp right here. 3 milliamp right here. 1.5 milliamp here. 1 milliamp right here. And then everything else is a fraction of a milliamp. Voltage. What do I have range-wise? From 0 to almost 3. Do you agree? So 1, 2, 3. Put 4 here. Now it is up. You see, even in a rough drawing, you have scale. You got it? Okay, and then I'm going to pick up a few points. At 0, I'm going to draw it here. I'm just going to draw points first. At 0, I'm here at 12 million. Here's 1 point. At 0.7 volts, which is about right here. So this is 0.5, 0.6, 0.7 right here. I have 7.1 million. So 6. So I'm going to be right here somewhere. And then I'll go to the next one is minus 1.7. 1.7 right here. And I have 2.1. So if this is 1.5, 2 is here, 2 is here, 3 is here, and that's 2. Then I'm right here. And at minus 2.5, I have 0.03 somewhere right here. And almost 3, I am right here. So if I had to draw this, this is definitely not a straight line, but a what? A curve. You with me so far? And that's the transconductance.
That's okay.
Yeah, that's pretty good. good at transconductors. I can work with this. I'm not going to create a hot monitor with this, kill the patient in a heartbeat. But it's good enough for any point. Does that make sense? For a control circuit or something of that nature. Is everybody starting to get the picture now? Now, why do we want the transconductors? That's the thing. After that, it's a matter of, on this line here, based on these parameters, I can pick an RS to be somewhere where I want to be. That's the engineering part. Leave everything else, just play with RS. Get it to a point where you want to be. Does that make sense? And we usually like to be right somewhere around here, the upper 1/3. Why? Because when you do a tangent, it's steeper there. So you have a better deflection of the input signal to the output when we're ready to do AC. Do not worry about AC yet. You with me so far? We just know that's where it's heading. We're still in the DC world. Are we clear? So don't panic about AC and how the signal looks. Just know that it's on purpose so we can have an operating point that will ultimately give us the optimal control of the signal, the AC signal, from input to output. Especially when you're using it as an amplifier. Everybody got the picture? I'm going to go through attendance again. Yep.
Always going to be in quadrant 2.
Yes. So for transconductors, it's going to be that for a depletion zone. What is it going to be for an enhancement? Quadrant 1. Does that make sense? Right? So, yep.
This is quadrant 2 or 4.
This is quadrant 2. So 1, 2, 3, and 4 is it.
Oh.
Does that make sense? Okay. All right. So everybody saw what I just did here, but you need to be a little more precise. And I actually put in the spreadsheet. I put these numbers in the spreadsheet, and it drew for me exactly how that curve is. But then you have to verify. Now, unfortunately, you don't have a JFET in your kit, so you're not going to be able to do the lab physically, but you will definitely need to do it this way. Got it? And start thinking about what is it exactly you're measuring and how you're measuring it. Got it? So let me kill this. Don't need to save. Let's go back to attendance. Now, let's see who I was missing. Elijah. Isaac.
Here.
Teres. James. Guy.
Here.
Stefan.
You can go back.
Okay. Mason. Mason. All right, fantastic. Go work on the lab now. So